Welcome to a lesson with Dr. Powell. Let's take a look at this limit right here. The limit as x, y together approaches 0, 0 of, and let's do sine of x minus sine of y all over x minus y. We can expect this perhaps to be the slope of the tangent line on sine of x at 0, which there's a slope of 1 right there, or it's just the cosine of 0, which is 1, because cosine is the derivative of sine. So we should expect this limit to be 1. Let's see if that's actually what we get, but let's use L'Hopital's rule in some sense. Wait, L'Hopital's rule? We can't do that. We got two variables. Yes, we have two variables. So we better use maybe a chain rule in order to make it one variable. So what we could think is so that it would actually apply. So why don't we let x be equal to f of t? Let's let y be equal to g of t. All right. And so, and we're going to let f and g be completely arbitrary. We only want, the only thing that we're going to fix for f and g is that these guys will both go to 0 as t heads towards something. It doesn't matter what t heads towards. We'll just say a, it doesn't really matter. But we just require that as t heads there, that both of these guys go to 0. And we need to keep this arbitrary. The reason why we need to is because we need every single x, y value that's getting close to the point 0, 0, like everywhere around, to be getting close to the limit. So kind of circularly from every direction, going every which way, no matter how we travel to 0, 0, we better be getting to the same thing. So that's why we're going to let f and g be completely arbitrary. Now that's kind of funny for a calculation. You know, we're making this replacement, but not knowing what it is. But we'll see in a minute how it actually pans out just fine. Okay, so what we're going to do then is think of the chain rule. We have a matrix product, thinking of the gradient or the derivative here, or the gradient. So we have cosine x, and I'll just write it as a matrix, so just use a space here. And then negative cosine y. And then matrix multiply that to, well, since we're taking a derivative, we need we have x prime and y prime. But let's replace x and y with what they are, f and g. And just notationally, I'll just write an f and a g here. Okay, just think of this as being f of t and g of t, just simpler to write. And then here, I'll just think of this as, this will be f prime and g prime, okay, as a dot product. Now down here, I do the same thing. Okay, we get a 1 and a negative 1. And then we have f prime, g prime. Okay, again, using the chain rule here for x and y and what they are, and the derivative with respect to x is 1 and negative 1. Okay, so this right here. Now, why can we use L'Hopital's rule first of all? That's because as t approaches a, or then this is going to 0, that's going to 0, and the top of this is going to 0, and the bottom of this is going to 0. So you have to realize that's why we're using L'Hopital's rule, because top 0, bottom 0. Okay, so now let's see what happens now with that dot product. We get cosine f, we put an f prime here, minus g prime cosine g, and then we put all this over. See, it looks like it's just f prime minus g prime. Notice something interesting. We know that f and g are both going to 0. Now, so we can plug them in right now. Notice if we plug in both f and g going to 0 right now, look what happens. It doesn't matter what f and g are. We'll notice something very interesting. F and g going to 0 makes this guy go to 1, that guy go to 1, because cosine of 0 is 1. So we end up getting f prime minus g prime over f prime minus g prime. Oh my goodness. Without even knowing what f and g are, look what happens. And the limit is 1 as desired. Using LHopitals rule and a substitution, arbitrary substitution, so that we could go from any direction to that particular input point. And we got a limit of 1. Thanks for watching.